After looking at the intersection of two planes, we now move on to three planes, which is not a new concept, as this is similar to solving a system of three equations, but now you understand what those three system of equations represent. They actually represent planes in 3D. So you basically can solve the three planes intersection the same way you'd solve the system of three equations. So either using substitution, Gaussian elimination, or using the GDC. And then based on the answer, you'll be able to know what type of intersection you have. So we either get a unique solution, so they intersect at a single point, or we get infinitely many solution, meaning they intersect at a single line, and that line is represented by a parameter. Or we get no solutions, and no solutions can happen for three different reasons, either because all three lines are parallel, or two lines are parallel, or a pair of lines intersect at a line. Two planes intersect at a line. So you can see these two planes intersect at a line, these two at a line, these two at a line, but none of them at the same line or point. So we'll look at three different examples and three different ways to solve them. But again, the solution to these are not unusual. You've dealt with them if you've done system of three equations. So how to approach the questions. If I'm given three planes such as these, if I am looking for a unique solution, then they would have one common point. If there would be no solution, then there would be no common point. The planes form a triangular prism, or infinitely many solutions, they intersect to a line, or at least two planes coincide. This is another illustration, so for the different situations, you can pause and have a read through it as well. So let's go through this example. So I need the point of intersection between the planes. So they're already telling me that it's the first situation where they meet at a single point, not a line, a single point. So how would you solve this in this case? Well, you solve it like a normal system of three equations. You start by trying to eliminate values. You can take two planes at a time, but you need to use a combination of all three planes. So I will go and add plane 1 and plane 2, and that just so I can eliminate the z. So I will get this will end up giving me 3x minus y equals to 1. And then I can also, now I need to do another combination, but I need to use up the third plane. So again, recall how you solve system of three equations. So the way I'm going to do that is I'm going to take 4 times the second plane, and I'm going to add it to plane 3. And when I simplify that, it's going to give me 11x minus 11y equals to negative 11. So now I've eliminated the z, and I can continue to try and solve. So I'm going to what I'm going to do is I'm going to take the first equation and make y the subject. So I end up with 3x minus 1. And then using this 3x minus 1, I'm going to substitute it here. So I end up with 11x minus 3. And then let's just immediately expand out. It's going to be 33x minus, plus 11 equals to minus 11. And then as you try and solve this, you'll end up with x equals to 1. So we're not getting x we're not getting y in terms of x. We can actually find a value of x, so we can immediately see that, okay, we are getting a solution or a possible point of intersection for this. So now that I've found the x, I can replace it into the y to find the y value. So that's going to give me a 2. And then go back to one of the equations here. Plane 2 is easiest to use, or plane 1 actually. So this will be z is equal to x plus 2y minus 4. And I can replace the x and y values that I found, and that will give me z to be equal to 1. So based on this we can then conclude that the point of intersection is 1, 2, and 1. And you can check that using the GDC, where you go to apps and you have your simultaneous equation solver. You pick 3 equations, 3 unknowns, replace the values in there, and you should get the solution 1, 2, and 1. I'm not going to do that because that's quite straightforward to do. So let's have a look at this. So we have this time I want to determine a parameter so that they intersect at a point. So a unique solution has to exist. And again, this is not new. This is something that has been discussed and done in a system of 3 equations. So you can approach it the same way as we did for system of 3 equations. And then you end up with trying to figure out a value of m that will not give you an error. So it still works and it's still a correct method. What I'm going to do is I'm going to approach it using a vector method. So again, both methods are correct, whether you do it purely algebraically or using vectors. So for the vector method, what we're going to do is we're going to find, well, we know they should intersect at a point, so let's initiate where these two will intersect. I know the nice values of these two, so this is similar to part 1 of this lesson, where we have where we try and figure out where 2 planes intersect. So you can have a look at that video. I'm not going to go through the full detail of the method because it's already discussed in part 1. But what I have done is I've eliminated I've made x the lambda. So as I'm trying to find the intersection between these two, plane 1 and plane 2, I end up with a x being lambda, and then y being a negative 16 plus 5 lambda, and z being 43 minus 13 lambda. I like to write the lambdas later because it gives me an easier way to write this in vector form. So we have no constant here, so 0, minus 16, 43, plus lambda, 1, 5, and minus 13. So this is the vector equation of the line that they both go through. Now, I need the point where the plane would intersect. Well, if we go back to the diagram just to see what it looks like so far, we are in this situation. We have this intersection. Let me use a different color. So we have the intersection of the 2 planes here, and we know the direction vector here between the 2 planes. But I need this 3rd plane not to be in this situation where you have infinitely many solutions. I need it to be flat, such that if you notice, if this is my line, it means it has this direction vector, but this direction vector, and I have this plane, so let's say this plane has this normal vector, they have to be parallel, or in other words, they cannot be perpendicular, because if they were perpendicular, you'd be in this situation where the 3 planes would intersect at a line. And what I'm looking for is that they intersect at a point. So if I found this line, but I'm trying to make sure that this line is not perpendicular to my 3rd plane. So I'm trying to make it parallel to my 3rd plane. So what I'm going to do is I need to make sure that this direction vector, let's go back to normal colors. So I need to make sure that this direction vector, so 1, 5, and negative 13, with the normal of the 3rd plane, which is 4, m, and minus 4, is not equal to 0. because if they were equal to 0, it means they are perpendicular, and then you're in the infinite solutions. And we want a unique solution. We want them to be parallel, not perpendicular. So in this case, if I don't want them to be perpendicular, it means I do not want their scalar product to be equal to 0. So this is what I'm looking for, which means that I don't want 4 plus 5m plus 52. I don't want it to be equal to 0. And when you're solving for m, you end up with negative 56 over 5. Sorry, m cannot be equal to negative 56 over 5. So the values of m, so that the plane intersects at a point, it's m, all the real numbers, but m cannot be equal to 56 over 5. So that's the solution to this. Now we'll head to a slightly different question, a bit unusual, but hopefully step by step I'll make it clear on how to approach this question. So we're looking at 3 planes, and we're looking at them intersecting in one line. Now, one line meaning they have infinitely many solutions. Now the issue is I have 3 unknown parameters here, so I can't approach it exactly like the previous question. Plus I'm looking at one line, not one point. So what do we do in this case? Well, we approach it again the same way we approach the previous question, which is take the first 2 planes that you have, that you know all the values of. Let's find the line that they intersect at. And it's the same method as part 1, where we look at, we try and make one of the letters the lambda, or the parameter. And what I've done is I've made z my lambda. So you end up with an x equals to 6 over 5 plus 4 over 5 lambda, and a y equals to a negative 7 over 5 plus 7 over 5 lambda, and z equals to lambda. So then if I'm writing my, instead of parametric form, if I'm writing it in vector form, so I end up with a 6 over 5, negative 7 over 5, and a 0 here, plus a lambda, 4 over 5, 7 over 5, and 1. So now this is my line, and I want to make sure that this line also fits in with my 3rd plane. So this is my original line that I'm looking at. So how would I do that? Well, first of all, let's look at how we can determine A, B, and C. Now A, B, and C are the normal, and I need to look at the behavior of the normal of my plane and the direction vector. Remember, this is the direction vector of my line. Well, going back to the diagram, if this is my line, then if you notice, it has the direction vector here. And if you look at this direction vector with every other plane, you'll notice that it will be perpendicular to the normal of all the planes there. So it is normal to this plane here, it is normal to this plane here, and it is normal to the 3rd plane here. So it is normal to all 3 planes. So we're looking at this being normal to having a scalar product of 0 with the normal of the 3rd plane. So the direction vector here, let's take a nicer value of it. The direction vector is 4 over 5, 7 over 5, and 1. But you can actually take out a factor of 1 over 5 and end up with 4, 7, and 5. It's just a nicer direction vector to deal with here. We're not replacing it in the original, keep that in mind. We're just picking this for now. Now, how do you find a normal here that would fit? So a normal. Now, there are infinitely many. Keep that in mind. There are infinitely many vectors that are normal to this 4, 7, 5. And there isn't a foolproof method to find one. I will write out one method, one way to find it, but you still need to check that you get correct values and you don't accidentally end up with zeros all around. So, for example, if you have A1, A2, A3, one possible normal vector could be you taking A3, A3, and then a negative A1, A2. That's one possibility. So this would, if you take a scalar product of these two, they would be 0. Another possible combination is A1, A1, and then minus A2 minus A3. And another combination is A2, A2 minus A3 minus A1. Now, these combinations, again, there are some flaws to them, so don't take them as guaranteed ways, but it's one possible approach or one head start to finding the normal to the plane. So if I have 4, 7, and 5, I'll try this combination here, and I will get a negative 12, 4, and 4. Now, I can make it nicer. I can take out a factor just like I did here. I can take out a factor of negative 1, and I end up, negative 4, and I end up with a 3 minus 1 minus 1. So I can use this as my normal vector. And I can check. I can take the scalar product, so 4, 7, and 5 with a scalar product of 3 minus 1 minus 1, and it should give me a 0. So I end up with having a normal vector there, which means I have found my A, B, and C values. All right, we found the A, B, and C values, but how do we find this D value? Well, we need a point on the line, so a point from this line that would fit into this such that we can find D. So if I look at this equation and if I try to find a point on the line, well, to find a point on the line, you just need to replace, you get a scalar multiple. So if I try lambda equals to 1, for example, what I get, x, y, and z, will just be equal to 0 and 1. So that's a point on the line. And again, we're looking at the original line, not where we took a scalar multiple out. So by having a point on the line, and I have A, B, and C, so I have 3x minus y minus z equals to D, and I have a point on the line, so I can replace it there, minus 1, and that's going to give me D being equal to 5. Once I have that, I can then say that plane 3 is just basically 3x minus y minus z equals to 5. And how do you check your answer given a GDC? Well, you put them all into your, you put those 3 into your system of 3 equations. So 3 equations, 3 unknowns, and we can replace them in there. So we have a 3, a minus 1, and a minus 1, and it gives me 5. And when we solve, you notice we get the line that they all intersect in, which is the line we found with the first 2 equations. And all we did was trying to fit that into our third plane. Now, the numbers you previously saw before I erased this was actually me using a different combination of the normal plane here and getting a different plane. So I got a different plane here if I use a different normal vector. I tried using this combination, and I got another plane with 5 minus 11z equals to minus 1. And when I put this into my plane as well, into the equation on the GDC, I also got the line that we found here. I still got the same, I got the same solution here. So just to point out that the plane, the third plane, is not unique. You can have different representations of the plane. That's only because the normal that we pick is also arbitrary. But they should all, even though it's a different plane, so even those two might look different, they are possible planes, but they should all give you the same solution here where they intersect at this line. So hopefully the examples were clear. This example is a bit of a unique one, but it encompasses a lot of different concepts, so hopefully it was helpful.